What if I told you the speed boost for your app has nothing to do with the frameworks or servers that you use for it, but has everything to do with the way you store the data? Stick around because I'm going to cover the top 5 data structures that every software engineer should know and also how to use them in real projects. Hi, I'm Edna. Welcome to my channel. I have created this space so I can help other software professionals grow their skills and become more productive by using AI powered tools and workflows. I've been in tech for over a decade now, and I've experienced it all: the promotions, a layoff, and burnout. I never forget the morning when I couldn't access my account anymore. And I thought to myself, I must have finally broken VPN, right? Because I have too many tabs open on Chrome. But then Slack messages started coming in, and I realized that I was laid off. That moment made me kind of view my career from a different lens and made me decide to create this space for real talk and real growth. I publish videos every week. Go ahead and subscribe so you won't miss out. Think of data structures as the blueprint for how your app stores and organizes data. Use the right one, and your app is going to be fast and lean. Use the wrong one, and it's like you put a toad in a fast moving car because you're not going to get far with it in your car, right? Here is an example. Instagram was able to increase the loading time for their Explore feed by 50% by switching from using array data structures to lookup structures. And that's basically what kind of performance efficiency and boost we're talking about here. Let's get started with arrays. Arrays store data in a fixed order side by side in memory. For example, if you want to reach and get the third item in the array, it's very simple, like basically O of one. You just call it and you have it. So arrays are really good if your data size is predictable, but also that you have a lot more read operations than write operations. Meaning like you don't do a lot of deleting or inserting, let's say, in the middle of the array, because that's when things go south because you have to shift everything. And that's why the complexity jumps from O of 1 to O of n. Arrays are basically like a very well kept and labeled bookshelf. Very quick and easy to go and get the one you want. But all my things get annoying when you need to squeeze everything in the middle so that you can make space for that new book. A real world example is Instagram's feed. They save each of the posts with the specific post ID in an array. And then when you're scrolling through your feed, they go and fetch those by the ID from the server. Here, I'm creating an array with 4 numbers. Arrays store items in order. So R2 means give me the third item, and it gives it instantly. That's O1 as we talked before. So it's pretty simple and quick for time complexity. Now, if you want to insert 99 between 1 and 2, well, in this case, I use splice 1099 function. That says starting at index 1, remove 0 items, and also insert 99. But here's the catch: everything after index 1 has to shift over in memory. That is why inserting in the middle has the time complexity of O of n, because the more elements you have, the more shifting needs to happen. If you've enjoyed this video so far, I would really appreciate it if you like it, comment, and share it. And also, if you haven't subscribed to my channel already, go ahead and hit that subscribe button. It helps a lot to grow the channel, but also to show this content to others who might find it useful. And in return, I promise I will answer all of your comments, but also, here's a cute picture of my dog Caden. Isn't he so adorable? Also, by the way, new background. How do you like it? Let me know in the comments. Hash tables, or also known as dictionaries, are the type that store in key value pair. So you give it a key, and then the hashing table calculates and figures out based on that key where the value associated with that is stored in memory of your computer. So that's why most of the time the retrieval process is the time complexity for that is O of one because it takes just one operation. But sometimes things go a little, not as smoothly where there's a what we call the hashing collision, and so the retrieval process becomes O of n, like the time complexity, because there's then a linked list associated with that memory location. By the way, we're gonna go over the linked list next. Hash tables are like a locker room with your friends' names on each as the key, with their belongings as the values associated in that locker. But what happens when two people have the same name? Yeah. Also, in real world, you can think of it as an e-commerce like Amazon. They store product IDs as the key, and when you go and search for it, blue shiny shoes, it's like a key. It goes and fetches all the product details based on that. Oh my, it would have been a nightmare if it did like had to scan the whole catalog and search for the what you wanted. It would have been very slow. So with hashing tables, it's a lot faster. Here I'm creating a hash table using a plain JavaScript object. The key is the name Alice, and the value is an object with her city. When I type profiles Alice, the hash function under the hood instantly maps that key to a memory location and returns her profile. That is why it's O of 1 for time complexity on average. Then adding Bob is just as quick. You give it the label and it stores the value. And if we no longer need Alice, we can just delete and remove her entry. The magic is you never have to loop through all the data like you would in an array. So if you know the key, you get the value instantly. Linked lists. They are basically a chain of nodes that one is connected to the other. So it's fairly easy to kind of go ahead and add or delete the nodes, especially at the beginning and end. But things get a little more difficult and more time consuming, so greater than sometimes O of n, when you're trying to access and read a node, because you have to walk through the linked list node by node until you find what you're looking for. Linked lists are like a treasure hunt. You go and look for the clues one by one, right? Chain of nodes until you find what you're looking for. And that's kind of the difference with arrays because they're kind of related and chained together. A real world example is when you do undo and redo in Word document, for example, because each of those actions and saves that you do, they get saved in the linked list. So usually at the front, right? So the latest is in the front. And when you click on undo, it goes backwards one action. And that is how you can do 1,000, undos and redos like very fast and it's very smooth. First, I'm making a node class. It holds the data and a pointer to the next node, which starts as null. I create the first node with the value 10, and that becomes our head, the start of the list. Then I set head.next to a new node with the value 20. Now we have a chain. 10 value points to the 20 value. If I want to add something at the start, I can just create a new node and point it to the old head. No shifting is required like in arrays. It's just changing a pointer to point to the new one, right? So that's why inserting and deleting in the middle is even easier than arrays. But let's cover stacks and queues. Stacks is basically, you put things and stack on top of each other. The one that goes first moves out last, and the one that is last moves out first. It's kind of like the undo features we talked about earlier, but also like call stacks and backtracking. It's like when you have a stack of pancakes, you stack them on top of each other and you eat the first one, the last one that you put in first. Queues, on the other hand, are first in, first out. So it's basically when you're standing in a waiting for your coffee, to order coffee. The first person who is in the line first gets served and assisted first. Here is a real world example for stacks. Have you ever thought about your web browsers, like internet browser, like Chrome? The back button where it goes back to the history of your browsing, that is based on stacks. And for queues, have you ever thought about how printers work? So if you queued in a printing job after somebody who, I don't know, wanted to print 500 pages of novel, you have to wait for that person to finish printing and then yours will be printed next. First, the stack. Think of it as a pile of plates. You add to the top with push and remove from the top with pop. I push 1 and 2, and when I pop, it removes 2 because it was last in. So that's LIFO, last in, first out. Now the queue. I add task 1 and task 2 to the end. But when I use shift, the shift function, it removes the first item, task 1. And that is FIFO for you, first in, first out. Stacks are great for undo actions or backtracking, as I mentioned earlier. And queues are perfect for job scheduling, where the first job should be done first. Graphs are the last one we're going to cover, and they're like relationships. They have what we call nodes that represent things, places, people, and these things or nodes are connected to each other with connections, with relationships, which we call edges. Also, trees, the tree data structures that you're probably going to hear a lot about, also are a type of graphs. These connections or edges between the nodes, they can be directed or undirected. They can be weighted or unweighted. You can think of it as a city map. Basically, the places are nodes and the roads that connect these places are edges. You guessed it. A real world example for this is Google Maps. It's basically each intersection is a representation of a node, and the way the roads are connected, it's based off of the traffic time, right? So that's the weight for these connections. And what happens is, like, when you ask Google, hey, give me the quickest way to get to this destination, it runs it through what we call the shortest path algorithm, and that's how it figures out the route for you. Here I'm creating a graph using a list. Each key is a node, and the array lists all the nodes it's directly connected to. So A connects to B and C. B connects back to A and also to D. This lets you model things like roads between cities or friendships in a social network like Facebook. If I wanted to find all of A's neighbors, I just look up the graph A and I instantly know the direct connections. So for bigger graphs, though, you can run search algorithms like BFS or DFS, which are pretty popular also, to find the shortest paths or explore the network. If you enjoyed this video, I would really appreciate it if you like, comment, and also share it. Also, if you haven't subscribed to my channel already, go ahead and hit that subscribe button. I would really appreciate it because it helps the channel grow and also to show this content to others who might find it useful. And now I leave you, like I always do, with a joke because life is too short not to laugh. Why don't developers fight over data structures at lunch? Well, because they don't want to hash it out in public.